It's 1800 Pacific time, right on the dot.
Yes.
Thank you to everyone who's joined via Zoom and everyone who is watching on Facebook Live. My name is Joshua Gilliland, and I am the chairman of the Sea Scout Marketing Subcommittee. And we're going to have a lot of fun tonight with Doug Post to talk about piloting. Doug, it's 1801, which brings up our fun historical discussion that we can have about the beginning of the Jefferson administration. But tonight, let's focus on piloting instead. So, Vice Commodore Love, take it away.
Okay, good evening, ladies and gentlemen. Tonight's presentation will be on Ordinary Requirement 10, that's Ordinary Piloting, Part 1. I have a lot of material to cover, so I just want to jump into this very quickly. To start off with, the objectives is to acquaint the students with the rudiments of piloting, to determine a position using a set of coordinates, and to understand how a compass works and apply the appropriate compass corrections. So with that, and then finally to determine the speed of a vessel. So with that, we're going to go straight into Ordinary 10A, which is Latitude and Longitude. Okay, so to begin with, Latitude and Longitude is a grid system, an imaginary grid system, and it's based on the idea that wherever two lines intersect, you have a unique point. So that the basis of latitude and longitude is that every position on Earth can be expressed in a latitude and longitude. Latitude is expressed in degrees north or south of the equator. For me, since I'm in North America, almost all of my work in piloting and navigation is done in degrees north of the equator. If you happen to be watching this and you're somewhere south of the equator, like Brazil or Argentina or Australia or New Zealand, obviously most of your work would be south of the equator. Longitude, on the other hand, is an angular distance expressed east or west of the prime meridian, and we'll talk about that in just a minute. So, lines of latitude are called parallels, and they're called parallels because they are literally parallel lines, and they run from 0 degrees at the equator to 90 degrees at the north and south poles. Lines of longitude are called meridians because they're not parallel, and they converge at the north and south poles. They begin at the prime meridian, and they run 180 degrees, half a circle east or west of the prime meridian. Finally, the prime meridian is the line of longitude that runs through the Royal Observatory in Greenwich, England. The Greenwich meridian was designated as the prime meridian, or 0 degrees longitude, in an international conference in 1884. So before then, different countries measured longitude, distance east or west, based on varying meridians. Russia used one running through St. Petersburg, France, famously used one running through Paris. The United States briefly used one running through Washington, D.C. So this is kind of a basic schematic. So you have the equator, your x-axis would be your longitude, and it runs west for 180 degrees, east for 180 degrees. Your y-axis would be your latitude, and it runs from 90 degrees north to 90 degrees south. So if you were to draw this on a globe, thank you, Encyclopedia Britannica, this is an example of the grid for every 10 degrees. The prime meridian running all the way around, and the equator running all the way around, and then the parallels and the meridians based off of that. So when you are working with latitude, latitude is written as degrees, minutes, and seconds north or south of the equator. It can also be written as degrees, minutes, and decimal minutes, or degrees and decimal degrees. Generally, in maritime piloting, it's written either in degrees, minutes, and seconds, or in degrees, minutes, and decimal minutes. Degrees and decimal degrees are used primarily on the land-based side of navigation. So every degree equals 6 minutes of latitude. Now, every decimal minute equals 6 seconds of latitude. Common practice in the maritime industry today throughout the world is to write latitude in degrees, minutes, and then decimal minutes. So I give you an example here. This is actually the latitude where I am right now is 38 degrees, 28 minutes, 18 seconds north, would be equivalent to 38 degrees, 28.3 minutes north. There is no latitude greater than 90 degrees north or south, and I can't stress that enough. I've seen scouts over the years come up with these like 110 degrees latitude, and there's no such number. It doesn't exist. 90 degrees is either the North Pole or the South Pole. You can't go any farther above the equator than that. Longitude, again, is written as degrees, minutes, and seconds, east or west of the prime meridian. It can also be written, again, like latitude, in degrees, minutes, and decimal minutes, or degrees and decimal minutes. And again, each decimal degree equals 6 minutes because there's 60 seconds in an hour, basically, and each decimal minute equals 6 seconds because there's 60 seconds in a minute. Again, the common practice is to write in degrees, minutes, and decimal minutes. So this would be the longitude where I am right now, which is 122 degrees, 34 minutes, 36 seconds west, which actually equals, if I were to write it, my ship's log as 122, 34.6 minutes west. There is no longitude greater than 180 degrees east or west. And that's because there's 360 degrees in a circle. So if you take half of that, you come up with 180. Now, on a nautical chart, the latitude is found along the sides of the chart. The longitude is along the top and the bottom. And quite often, scouts will make the mistake of trying to get the latitude off the bottom and the longitude off the side, and it doesn't work. Now, one of the things you have to do is be able to find the latitude and longitude of a aid to navigation. So this actually is the easiest way to do it. So finding latitude is you take your dividers, put 1 point on the aid to navigation, 1 point on the nearest parallel, and then you simply move the dividers over to the scale and read your latitude from the left or right hand side of the chart. And that will give you the latitude of the item you're looking for. The same is true with longitude. You move put 1 point of your dividers on the aid to navigation, 1 point on the nearest meridian, move the dividers down along the meridian, and then you're able to read from the bottom of the chart the longitude. So for instance, this cabin headlight, if I go back one, you'll see here that this would be 45 degrees, 14 minutes, because it's not quite 15 minutes yet, And then if you count backwards, 1, 2, 3, that would be 0.7 minutes north. And if you look at the longitude here again, you can see it's not all the way to 81 degrees 20 minutes. It's actually at 81, 15, 16, 17.5. Quickest, easiest way to find latitude and longitude for a specific object. Now, I'll save all the questions for at the end, if you don't mind, only because I want to get through the material first. Okay, so 10B is all about compass. So the objectives for this part, you have to be able to explain the compass, the degree system of compass direction. You have to be able to explain variation and deviation. You have to be able to convert between true and compass direction using variation, deviation, and the converse, the reverse. So let's talk about compass direction. Compass is divided into 360 degrees, with north being 0, 0, east being 90, south being 180 degrees opposite north, west being at 270s. Directions can be expressed as degrees on the compass. And the mnemonic for this is real simple. It's never eat shredded wheat. It's north, east, south, and then west, progressing in a clockwise direction around the dial. Variation. Variation is the difference between true or geographic north and magnetic north, which is what is indicated by a magnetic compass. For those of you who have some orienteering, this is also known as declination if you're doing land navigation. And on the water, it's called variation. So how does this happen? Variation happens because the Earth's magnetic poles do not line up with the geographic poles. Part of that is because the Earth is tilted at 23 degrees roughly on its axis. So that variation also changes year to year. And that's because of changes in the Earth's rotation, changes in the orbit around the sun. Our Earth wobbles and has a slightly eccentric orbit, and the movement around of the magma around the Earth's core, which I'll explain in just a minute. Variation can be found on any compass rose of a nautical chart. So you have to picture the Earth as a giant electromagnet. In the center, you have this core, right? That is this extremely hot, extremely dense cupro iron nickel core. And around it, you have this molten rock. And this molten rock has currents and eddies and flows on its own. Not only that, but it has a rotational flow because as the Earth rotates, the liquid is imparted with a rotational movement. And if you want to demonstrate this, you can take a spoon, put it in a glass and stir it, and you can create your own little rotational movement. You guys have all done this. Now, all of this creates, because of that iron core, creates a magnetic field around the Earth, okay? That's kind of illustrated here. Now, deviation. Deviation is the deflection of your compass needle caused by electrical fields or large magnetic objects on your vessel. Okay? So, and it is dependent upon which way the vessel's facing, because that magnetic object will in effect move around your ship's compass and affect it in different ways. And you can demonstrate this by taking any compass and putting, a piece of steel next to it and move it around, and you can see that the needle will deflect varying amounts depending on where that piece of steel or a magnet is. So, how do we determine deviation? Well, deviation is determined by running a ship on predetermined magnetic courses and noting the difference between a magnetic course and the bearing on the ship's compass. And this is done over and over and over and over. And it's done first at 90-degree angles, and then at 45s, and then at 22 or 20-degree angles, and then at 15-degree angles. And you write all these down and you plot them out on a curve on a piece of graph paper. And then you can come up with what's called a deviation table. Now, every time you change a major source of electricity, or you change a major piece of machinery on a vessel, you should redo the deviation table. And there are also ways on small boat compasses, they have little adjustment screws where you can try and tune some of that deviation out. But this should be done every time. It should be done at least once a year on most vessels, because deviation is the one unknown. Variation is fairly constant. I mean, it changes year to year, and we have pretty good data on that, but deviation varies from vessel to vessel and what's on the vessel. A few years back, I had a skipper in my council who called me up, and we happened to be cruising together. And he said, "Can you come over here and take a look at my compass?" And I was like, "Why? What's going on?" He goes, "Man, it's way off and I can't figure it out." He goes, I don't understand. And so I went over and I looked, and I pulled out my bearing compass, and he had a gyro compass on his vessel, and we're looking at that. And his compass was 10s, 20s of degrees off. And I went, "Wow, this is really strange." I said, "When did this happen?" He goes, "It was fine. And then we tied up, where we're tied up. And this morning I get up and it's a mess." And what he didn't realize was that some of his crew had been working on a piece of equipment on the bridge and left a couple of screwdrivers and a wrench right by the compass. So I'm looking at this going, I go, "Well, what about these things?" And we moved them, and all of a sudden everything snapped back into place. So you have to be very careful around magnetic compasses, because even things like key rings, laptop computers with their speakers, tools, all of a sudden will just put this massive amount of error into a compass. And what had happened with the skipper is he just got up and looked at it, and he had tunnel vision, didn't realize that there was this stuff that was around his compass that was causing this great deviation error. And with another set of eyes, we solved the problem. So here's an example of a deviation table, right? So you can see that you have a magnetic course, the deviation, and then a compass course. The compass course would be the course that you would steer per the ship's compass if you wanted to maintain these various magnetic courses, which you have calculated from a true course. Now, please don't use this as a deviation table on your own vessel. This is just one that we use quite often out here on the West Coast to train, to use for the scouts to practice with, so they could figure out how to correct from true to compass and compass to true. This is in no means a deviation table for any given vessel. So, how do we correct the course if we have all these errors? Well, if you have a true course and you want to figure out what your compass course is, you go true, and then you add or subtract your variation. That gives you a magnetic course, which if we go back one, you can see that would give you the course that you would then look up to find your deviation. Then you would add or subtract your deviation, and that would give you your compass course. And in this case, going from true to compass, you always add west. Out where I am in the San Francisco Bay Area, one of our mnemonics for this is turquoise violates my dress code at weddings. So if you go to a wedding and you show up wearing, a turquoise tux or turquoise dress, you may be dressed a little out of place. Now, from compass to true is the reverse of that. Let's say you have a compass course, you want to figure out what your true course was. You take your compass course, you would add or subtract your deviation from the deviation table. That would give you a magnetic course. Then you would have your variation already figured out. You would add or subtract that, and that would give you your true course. And then in this case, you would always add east because in the previous, you added west. If you're going in the reverse, you would do the reverse, you would add east. So the mnemonic for this, of course, is can dead men vote twice at elections? So it's compass, deviation, magnetic, variation, true, add east. Okay. Next, I've given you a couple of examples here. So if I am going from true to compass, and this is the variation actually set up for where I am right now in sunny California. The true course that I have would be 247. Let's say I wanted to go on a course of 247 degrees. The variation is 13 degrees and 22 minutes east. My magnetic course would be 233 degrees 38 minutes. My deviation, if I go back to the table, a couple of slides back here at 233, which is closer to 240, right, is 8 degrees east. So that gives me a compass course of 225 because I have to subtract because I'm adding west. So I subtract east, 38 seconds. So to round that out into decimals to the nearest tenth, it's approximately 225.6 degrees. Or if I were actually telling one of my scouts to steer this course using a magnetic compass, I would tell him to steer compass course 225 or 226, depending on how the boat was being set, whether it was being set one way or another. We'll talk about set and drift at a later time. So when going from true to compass, always add west and subtract east. And the way to remember that is west is best when you're going from true to compass. Compass, it's the exact reverse. So I have a compass course of 138 degrees. My deviation, according to the deviation table, I'm not going to flip back to it again, would be 0 degrees. So my magnetic course, I would then add in, because I'm adding east this time, my variation, which would be 151.22, which would give me a true course of 151.4. And if I were steering the vessel, I would tell the scout to steer a course of 151, 150, 152, depending again on watching the set and the drift of the vessel. So when you're going from compass to true, always add east, subtract west. When you're going from true to compass, add west, subtract east. And the way to remember this again is west is best, east is least when you're going from true to compass. Speed. Okay, so the objectives here. The scout should be able to name 3 devices used aboard his or her vessel to measure speed. If possible, the scout should demonstrate the use of these devices. And I say if possible, because where I am right now, we're still pretty much on a fairly strict lockdown. I know a lot of ships have not been cruising, so it's really hard to demonstrate these devices in determining speed at this point. So let's talk about determining speed. There are many ways to determine the speed of the vessel. Okay. Um, there are 2 types of speed that you have to be aware of: speed through the water, speed over the ground. Um, Devices like a chip log or a speedometer measure speed through the water, and that is the speed of your vessel plus or minus the current, depending on whether or not you're going with the current or you're going against the current. Okay. Speed over the ground is the actual speed you're making towards your destination. So, any of these devices can be used to measure the speed of a vessel: a GPS receiver, radar, a stopwatch. You can time how long it takes you to go between 2 navigation aids that are fixed, or 2 landmarks. A chip log, which again is a piece of wood attached to a knotted string. You count the number of knots that roll out in 15 seconds, and that gives you a rough approximation of your vessel speed. A patent log, which is like a chip log, except it has an impeller attached to a line, which is put over the side and then allowed to spin, and it will actually register approximately the ship's speed again through the water. And then finally, a speedometer. Those of you who have ski boats have seen these before, where they have a little pitot tube that measures the pressure, and that gives you an approximation of the speed. Or those of you who have sailboats, you may have the long plastic tube that's frosted on the inside, and you put it over the side of the boat, and you pull it up, and it give you an approximate speed based on how high the water has risen. Or it may even have a little ball trapped in it that you can actually read against a fixed line. Any of those things can be used to measure a vessel speed. So, how do we determine speed? How do we calculate it? Well, there's a very simple formula. And this is about the only math we're going to get into, other than addition and subtraction. This is the multiplication part. Okay. It is 60D equals ST. The mnemonic, very simple: 60D straight. So D is equal to the distance traveled, S is the speed, and T is the time in minutes. To solve for speed, which is what you're going to need to know to do some piloting, because especially if you're a scout, your skipper will be like, okay, so how far is it to go from point A to point B? And you have already measured that out on the chart using your dividers, which we'll talk about in part 2. And then you'll do this little calculation. So it's 60 times the distance divided by the time in minutes is equal to the speed you're going to go. Okay. Now, if you have the speed, you can figure out how long it's going to take you to get there. And I'll show you that in a minute. And then you can say, hey, skipper, we're going to leave here at noon, and we're going to be at this point by 1300, or whatever time. So this is an example. So, and these are actual real examples that I pulled out of a notebook I kept last year on a cruise. So, how long does it take me to go from one day marker to another? And I know that the day markers are a half nautical mile apart. It took us 4 minutes. So I did 60D 60 times 1/2 mile is equal to 30. And then 30 divided by 4 is 7.5. So I knew the vessel at that point was making 7.5 knots. Now, did I know that? Here's how you would tell your skipper, how long it's going to take you to get somewhere. So now that I know the speed, right, I can then use the formula to figure out how long it's going to take me to go any distance. So I go 60D, and in this case, it was 12 nautical miles away. We were on a long reach up the San Pablo Bay, up towards, actually right past my house. So I knew we were making 7.5 knots. We had this long run of 12 nautical miles. So you just use the equation. 60 times the distance, 60 times 12 is 720. And I divided that by 7.5, which gave me 96. So I knew it was going to take me 96 minutes or 1 hour and 36 minutes to go this 12 nautical miles. So really, for the basics of piloting at this point, I mean, so far all we've done is addition, subtraction, a little estimation and rounding, and some basic multiplication. So this is the last example I have for you, and I realize this is short tonight, and we'll have plenty of time for questions. The speed time formula can also be used to compute the distance you have traveled, so that if I know I'm making 7.5 knots and I've been underway for 45 minutes, I can use this again. Speed times time divided by 60. So I have 7.5 times 45 gives me a number, 337.5. 337.5 is roughly 5.625. So in 45 minutes, I should have traveled roughly 5.6 nautical miles. Now, that's the last example I have. If there are some questions out there, I'll gladly take them now. Do we have any questions, Josh?
Not yet. So for those who might have a question, please type them in to the Q&A box that we have, and we will do our best to answer those for you. Now, Doug, just for those who don't know you, how many times have you cruised up and down the California coast with Sea Scouts?
More than I care to count. I have been everywhere from Vancouver, British Columbia to San Quintin, Mexico on a Sea Scout vessel. And I've probably made well over, in my Sea Scout career, 20 coastal cruises.
What was your favorite?
I think my favorite, well, I actually have three. One was when we went to San Quintin, Mexico, because actually being able to cruise down there, I have this fantastic memory of being anchored in this little Bahia San Quintin, in this little island, and called Isla San Quintin, and there's this little cove there, and these fishermen came out and rowed out, and they traded us 220 pounds of fresh caught yellowtail tuna fillets for 20 liters of water. They'd run out of water. So
Wow.
we gave 20 liters of water. The other one, the second favorite one was probably actually pulling into the harbor in Victoria, British Columbia, right opposite the ferry terminal, um, and docking right at the foot of the Empress Hotel there. Um, it's just a beautiful place, and everything you wanted to see in Victoria was pretty much within walking distance. But my all-time favorite memory was going up the Columbia River one year, and we had pulled out of Cathlamet, Washington, and it was cold and overcast and kind of your typical Washington, Oregon weather, where there was just these low-hanging clouds and everything, and we started heading upriver, and this brilliant shaft of sunlight just broke through and illuminated the side of the Columbia River Gorge.
Nice.
And it almost looked like one of the Albert Bierstadt paintings, right, from the 1800s, where they're using this light to illuminate. And it was absolutely one of the most beautiful things I've ever seen.
Awesome. And all of that thanks to piloting. So we have two questions. The
Certainly.
first is, what calculators are the best for piloting?
Honestly, I use a TI-30 if I'm using a calculator, and I just plug the numbers in. They also could give you, you could convert from degrees, minutes, and seconds to decimal degrees on them. Um, and I also use a nautical slide rule made by Williams and Plath, um, for doing speed, time, and distance calculations. Um, but honestly, I do most of my calculations on for this kind of piloting on a piece of. I have uh, honestly something like this, a little field notes book, right, where you can do this.
Cool. Now, are there any smartphone apps that you recommend?
Well, here's the thing. Yes, there are iNavix if you have an Apple product. There are several in the Android world, none of which I've really found too. They're a little more clunky. Um, so I would do a little D. I would look online, but I've used iNavix on my phone and on iPads before, but that whole electronic navigation is part of the last part of Ordinary and then into Able, which we'll talk about at a later date.
All righty. And when it comes to scratch paper, do you, the question gets into, do you have a separate mechanical calculator? Which I think would mean nautical slide rule, paper and pencil, etc. Any?
Um, you could do it paper and pencil. I've used a nautical slide rule along with that. I can, because I've been doing this for a very long time, uh, I can work a nautical slide rule faster than most scouts can plug in the numbers into a calculator. And that just comes with practice. And quite honestly, I would start out doing the calculations on a piece of paper, writing TV, MDC, a little AW at the bottom, and doing them over and over and over until you get comfortable doing it that way. And then you can use the nautical, and then for speed, time, the same thing. Set up the the formula to solve what you're looking for, um, because honestly, that way you get to understand why and how these things relate to each other, as opposed to just plugging in some random numbers into a calculator. And I know, Josh, you've seen the same thing where um, we have scouts who are doing piloting and are using calculators, which is fine, but they forget to convert the decimals back into minutes. Doing that point one is really equal to 6 seconds kind of thing, and that can lead to big errors really, really quickly.
Yeah. Agreed. And I'm a big fan of your method of learning piloting from several years of judging piloting at regattas and seeing youth do math and prepare. So one other question is, how many Sea Scout vessels have you cruised aboard?
Let me think.
And while you're thinking, we do have someone from Santa Maria, Portatello, Idaho, checking in to say hi. And yes, the webinar is being recorded and will be available on Facebook and YouTube.
2, 3, 4, 5. 10.
Okay, wow.
If I count them all, including times I was loaned out as a pilot / navigator to other Sea Scout vessels. Yeah, it's close to 10 Sea Scout vessels here on the West Coast.
Cool. And we do have a question from a mate who used to do navigation on a battleship. Yes, one
Okay.
of those. And it's, the question is, have you used the 3-scale nomogram on the bottom of a maneuvering board?
Yes, I have. And as a matter of fact, I was going to talk about that when we get to able piloting and talk about radar navigation and plotting and how to figure out collision avoidance and that kind of thing.
Excellent. Well, Doug, thank you. This is the beginning of our piloting adventure. We will be back on Wednesday night for part 2. Please sign up. It's also on, there's a Facebook event with the registration link, or you can watch on Facebook Live. And of course, that will also be recorded. And we're looking at dates to do ABLE next month. So we
Right.
do have lots of fun training opportunities coming up, and to help everyone when they're ready to get back on the water. So
and Josh, if I can say one thing here, especially to the gentleman who is the navigator on a battleship, I have found in my experience over the years that piloting tends to be one of the hardest things for scouts to understand, especially if they have adult leaders who are not practiced in piloting themselves, right? So that you end up with a situation in which you have an adult leader trying to teach something they really don't have a good grasp on. I mean, I could have spent another 15 minutes talking about why we have agnostic lines and why there's magnetic variation and that kind of thing. But I want to make sure that what happens is the goal here eventually is that anybody who's pretty good at piloting should be able to walk onto any Sea Scout ship, look at a ship's log, look at their charts, and be able to go, I understand this. And that's really what this is about. Obviously, you have electives for celestial and all sorts of stuff that are way beyond the scope of this. But several years ago, Josh, you had me write up some course outlines, which I did, and ran them through some very highly respected instructors at Cal Maritime and other places, that I updated recently for the most recent version and of the Sea Scout manual and advancement. And I just want to make sure that everybody gets an idea of this. It is sort of a black art, but it's nothing that is too difficult that the average scout can't do, and do effectively. Okay, thank you.
excellent. There's one last question, and I'll help answer this. And it's, I live in South Sarasota County, Florida, there's very little deviation, perhaps 2 to 3 degrees. Can I just disregard the deviation altogether? And the answer is no, please don't do that.
As a matter of fact, I'll be talking about that in part 2. What happens when you the only time you can discount deviation, or I think he means variation here, declination.
I think so too. I think so too.
Okay. The issue is that you have to understand that there are basically every minute of latitude is equal to 1 nautical mile. So that every minute you're off on your course, basically every degree you're off could end up meaning that you're 60 miles by the end of your course, depending on how long it is, you could be as much as 60 to several hundred miles off, which is a pretty grievous error. And when I talk about more about UTC and universal time and longitude and how they relate, time zones, there's a famous case of a number of British Admiralty ships underestimating where they were, let's say, at a huge cost of life. So if you're figuring out variation, you have to include it, even if your variation is minimal. The only time that you ignore variation or deviation, and you don't ignore variation at all, is when you're taking a site with a handheld magnetic bearing compass. You assume deviation is 0 because you don't know what the deviation is. It's unknown. That's the only time, and that's something we do in able piloting. We'll talk about that later. But yeah, you cannot ignore variation or deviation when you're correcting your compass, because it very little errors can be magnified greatly.
Exactly. So thank you all for tuning in. Thank you, Doug, and everyone.
Thank you.
See you Wednesday evening for part 2. Take care. Thank you.
Good night.